Welcome to Reasonable Data Science. This video is part 7 in my series on how to use Jupyter for data science. In this video, we're going to be building a really fun classification decision tree to try and predict if a passenger survives or dies on the Titanic. If you've been following along in the video series, you'll remember that we've already imported a lot of libraries that we need. In order to use a classification decision tree, we're going to need to import two new libraries. The first one is the tree from the sklearn package, and the second is the decision tree classifier, also from the sklearn.tree library here. After you've loaded those two packages, you can then go and load the Titanic dataset, which we've been using also throughout this series. If you remember, the dataset we're using is different than the dataset you'll download from kaggle.com. I've already edited this sum, so I've replaced the missing values and I've taken off a few of the columns just to make it a bit easier to use throughout this video series. What I love about classification decision trees is that you actually do not need to create dummy variables like you do with logistic regression. And so for example, for p-class, all we're going to do is we're going to take the p-class column as is and stick it into our decision tree algorithm, and it should model it correctly. What you do need to do though is you still need to change any data that's text or categorical, such as male, female here, into ones and zeros. Otherwise, the decision tree will not be able to use that column because it cannot read text data. So what we can do is we can just write a simple if statement where we say df underscore df of gender equals np dot where of df and then gender. And then when it equals male, we're going to give it a 0. Otherwise, we're going to give it a 1. And then if you were to look at our data set again after we do that, it has changed the gender from text data to numeric data, which is what we need to be able to use this column in a classification decision tree. So after you get the data set prepped and ready, what we need to do now is build our X and our Y data sets, which we'll use those X and Y data sets to then build our training and our test data sets. So I'm going to first set up our Y data set, which is just a dependent variable we're trying to predict, which in this data set for Titanic is the survived column. So I'm going to say Y equals df of survived. Then I'm going to say X equals, and for this, I just want to, I'm going to say df.iloc colon 1 colon. And what that does, it's going to grab all the columns to the right of our survived column here, and you just grab all of those. That way we don't have to type all of them out. So let's run that. You won't see anything, but what we can then do is we can just say x underscore train, x underscore test, y underscore train, y underscore test, set that equal to the train underscore test underscore split function. And then we're say x comma y. Those are the two data sets we want to create our x train, x test, y train, and y test data sets from. We're then going to say test underscore size equals 0.2. So we're going to be taking 20% of our data set and moving it into our test data sets. So therefore, we're going to train the data, we're going to train our decision tree on 80% of the data. We're going to test it on 20% of our data. And then you want to set some sort of random underscore state equals 0. So if you ever want to go back and recreate this randomized 20% test data set, you can. You just have to specify random state equals 0 there. So let's run this and you won't see anything, but let's just look at our data sets to make sure that they look correct. So let's just say y underscore train dot head. And what we should see here is just the survived column because as we specified in our y, we only want the survived. What we should see under x underscore train dot heads, we should see all the columns except the survived columns. So we're seeing p-class, gender, age, and fare. And so it looks like we set up our x and our x, y training and test data sets correctly here. So after you set up your training, your test data sets, we now are able to build the decision tree that we want to model the data. So the first thing I'm going to do is I'm going to set up a new variable called dtree, which we're going to then stick our decision tree model into that variable. So I'm going to say dtree, and it's going to say decision tree classifier. And then within the decision tree classifier function, there's a couple things you need to specify. So the first is max underscore depth. I'm going to set that equal to 10. What that's going to do is going to limit the tree output to only having 10 levels below the root node of our tree. So it's a way to limit the size of the tree, which that way it won't blow up our decision tree for what we're learning here today. I'm also going to say min underscore samples underscore split equals 3. So what that means is I'm going to force the decision tree to not split the branches or the decision nodes until there's at least 3 data points in each decision node, and then it can split it further. If there's only 2 data points in a decision node, then it's going to stop. So after we run this, you won't see anything, but what we can then do is we can then fit the decision tree to our data. So this was just setting up the decision tree. Now we're going to fit the decision tree to our data. So we're going to say dtree equals dtree dot fit, and we're going to say x underscore train, double brackets, and for now I'm just going to use p class and gender as our variables that we're going to train it on, and then we're going to say y underscore train. And then when we run that, we won't see anything either. So you want to say dot fit, not dot fix. All right, so when you run that, you won't see anything either. But what we can then do is we can plot the decision tree. But before we do that, I like to do something that's completely not required, but it does make your tree a lot nicer to read, is set up the labels. So I'm going to say labels equals, and then you make sure you do exactly the order that you have it up here. So I'm going to say p class and then gender. And what this will do is it'll add labels to our decision tree, which will make it a lot easier to read. But just like I said, again, make sure that the order of these labels is the exact order that you had up in your decision tree when you fit it. All right, and then so now we're going to plot the tree. So I'm just going to limit the size of the tree here so it's a little bit easier to read on the screen. I'm going to just say fig equals plt dot figure. Then I'm going to say fig size equals 40, 10. You can adjust this on your screen however you see fit, but for my screen, I'm just going to use this so it's a bit easier for all of us to see. Next, I'm going to set up, I'm going to do tree.plot underscore tree. And then within this function, I'm going to say dtree, which is the name of our decision tree that we built up here. And then I'm going to say feature underscore names equals labels, which is the labels that we created right here. So those are going to be the feature names. Class underscore names equals, and then in brackets, I'm going to say 0, 1. So the order of our output is going to be the negative or the zeros followed by the ones in our decision nodes. And then I'm going to say filled equals true, just to make it a little bit nicer to read that way. To show the tree, we just say plt-show. And then when we run this, it might take a couple seconds on your screen, but we get a really nice decision tree output. So let's just go over what this decision tree output actually shows us here. So at the top is what's called the root node of the tree. This is the starting point of the tree. And so when you go to the left side of the tree, that's anything that's true. When you go to the right, that's anything that's false. And so how to read this is you start with the top term here. So it says gender is less than or equal to 0.5. So if we were modeling or wanted to follow the tree for a male passenger, remember up here in the beginning, we specified males as being 0, females are 1. So since males are 0, so 0 is less than or equal to 0.5, we're going to say true, and we're going to follow this branch here. Then we arrive at a decision node. And so from a decision node, you make a decision. So if your P class is less than or equal to 1.5, you'd go down this branch. If your P class was greater than 1.5, you'd go down this branch. And so if we had a male who was in first class, we would say 0 for gender is less than 0.5, true, go down this branch. If it was in first class, we'd say P class is less than or equal to 1.5, true. So we'd go down this branch here. And what this shows here is a leaf node, which is the end of that branch of the tree. And this is where you'll classify this passenger. And so since we specified up here class names 0, 1, what this value here shows is the number of zeros, the number of passengers that died, which is 64, compared to the number of passengers that lived, 29, in this leaf node here. And so since the leaf node takes the overall majority, it's going to label it class equals 0. And so if you were a male who was first class, we're going to classify you as having died on the Titanic. If you were a male who was in third class, you would then come down this. You would then instead at this decision node, you'd go to the false side. If you were in third class, you'd still follow the false side here because P class is greater than 2.5, and you'd arrive here. And so since there's 243 observations that died, 40 that lived, we would classify that passenger as having died on the Titanic. If you were a female, instead, the gender is 1, so you'd say false. 1 is not less than or equal to 0.5, so you'd say false. And then let's say you were first class, so your class is less than 2.5, true. P class is less than 1.5, true. You'd arrive down here. And in this leaf node, 3 of the observations died while 70 lived. So that passenger who was a female in first class would end up being classified as having survived the Titanic. So that's just a quick and easy example of how to read a decision tree output. But let's say we don't want to read the output. We would just want to use a function to get the output. What we can do is we can just set up a new variable called predictions. And then we're just going to say pd.dataFrame. And then in a little brace, we're going to say pclass : 2. And then we're going to say gender : 1. Close the brace, close the parenthesis there. And so remember, when you're entering what we're doing is we're creating a new data frame that has new variables we're going to predict. Just remember when you do this, make sure the order is the exact same as we have up here in our dtree function. Otherwise, you'll get the wrong values. So then what we're going to do is we're just going to say print dtree.predict. I'm just going to print predictions. So if we run that, what it outputs then is for a passenger who's second class and they're female, it outputs a 1. So that means they survived the Titanic. We can test that if we come up here and we say, okay, you're female, you're a 1, you go down this branch. You're second class, true, you're less than 2.5. Second class is greater than 1.5, go down here. 5 died, 57 lived, so yes, we're going to classify that passenger as having survived in the Titanic. Let's say you were a second class male instead, so we're going to put a 0 there. So we're going to run that and it outputs a 0. But again, we can test that because our D-tree or decision tree is very simple. So gender is 0, we're going to come down here. Class is greater than 1.5, true. Class is less than 2.5, true. So it looks like 72 passengers died, 14 lived. So a male who is second class, we're going to classify them as having died on the Titanic. So that was creating a decision tree using just two categorical variables, p-class and gender. If we wanted to look at adding in a non-categorical or a numeric value, we can just come up there and copy our same D tree that we created, and let's just add in the age variable here. And so when you run this, you won't see anything, but then what I'm going to do is I'm just going to come up here and copy our labels and add in age, and then copy the decision tree code here. And I'm going to run the labels, and then I'm going to run the decision tree as well. And this one might take a little bit longer to process because we're adding in a numeric column, which is going to cause a lot of different trees to be created. And just by adding in that one numeric column, you can see how quickly you can blow up a decision tree. It makes it pretty unreadable. So while our decision tree up here with two variables was easy to read, we could actually follow the decision tree and find a prediction. Down here, when we just add in one more column, you can see how quickly it blows it up and makes this tree pretty unreadable. So that's where using this prediction function becomes very handy when using D-trees, because as you can see, this is pretty unreadable. You can't even use this at all. And just imagine if you had 20 variables in your decision tree. You wouldn't be able to read that at all. So let's classify now a passenger who is second class, male, and who is the age of 32. So we're just going to say age, 32. And we run that, we get a prediction of 0. If I were to zoom way in here, we could probably still use this decision tree and follow it, but again, unreadable. So we're forced to using the equation here to figure out what our data set's classifying them as. So if we wanted to test how good this model was, this decision tree model that had p-class, gender, and age, how well it does when actually classifying the test data set, we're going to now take the decision tree and apply it to the test data set. But first, let's look at our test data sets again. We're going to say y_test.head, and that's the survived. x_test.head should be all of the columns except survived. And so how we can apply this decision tree we created to the test data set, we're first going to apply it, and then we're going to stick the predictions in a new column called predicted in our y_test data set. So we're going to say y_test predicted, set that equal to our D tree model that we created above. Then we're going to say .predict. And then what we're going to predict is x_test of p-class, gender, and age, because those are the only three variables that we used in our D tree so far. Close that off with the brackets and then a parenthesis. And then when you run this, we can look at our y_test.head, and that'll output either a 0 or a 1 in the predicted column. And so we can look at the 5 rows here and say, oh, this passenger survived, and we predicted they survived. But oh wait, this passenger survived, and we predicted that they died. So instead of looking at every single row, we can use what's called a confusion matrix. And so to create a confusion matrix, we can use the library confusion matrix display. So first of all, I'm going to set up a variable that we're going to stick our confusion matrix into, and I'm going to say confusion matrix equals confusion matrix display dot from_predictions. And then we're going to say y_test of survived. And then we're going to say y_test of predicted. And this is very important. You need to always specify your labels in a confusion matrix so that way you know the order of it. So we're going to say 0, 1. So we're going to start with the 0 values or the false values, and then we're going to go by the 1 values or the true values. I'm going to say color bar equals false. We don't need a color bar for this one, so that's just an optional argument. And then this one is also optional, but it really helps clean up and make the visualization of the confusion matrix easier. So I'm going to say display underscore labels equals died 0 and then survived 1. And then just close off that parenthesis. So that right there builds our confusion matrix, but I'm just going to add in a few other optional things just to make it a very nice looking confusion matrix. So I'm going to say plt.x label, or say predicted, plt.y label, I'm going to say actual, and I'm going to say ax equals conf matrix dot ax underscore, and then ax dot x axis dot tick underscore top. What we're doing is we're moving the x-axis to the top, so it's just easier to read. And then x dot x-axis dot set underscore label underscore position. I'm going to say top. And then finally, we're going to say plt.show. And what that does is it outputs a really nice confusion matrix where you can see the predicted values going across the top, the actual values going vertical here. So how do we read this confusion matrix? Well, as I mentioned, across the top is predicted. So in this top left cell, we predicted that passengers would die or they're a 0. And then we come down here and we compare it to the actual. Well, the actual shows they died or they're a 0. So 93 times we accurately predicted a passenger dying. If we come down here to the bottom right, that shows that we predicted the passenger survived or they're a 1. And then they actually survived or they're a 1. So we did that 48 times. So our model got 93 plus 48 of the records correct in our test data set here. So if we want to see the accuracy of our decision tree, we would say 93 plus 48 divided by 93 plus 14 plus 24 plus 48. So that's just a percentage of times it got correct. As you can see here, it's 78% of the time it was able to accurately classify the test data set. If instead of typing this in, there's also a function, we could just use metrics.accuracy underscore score. And then we would say y underscore test of survived, y underscore test of predicted. And that would give us the same 78%. While our decision tree was 78% accurate, unfortunately that means it has error in there. So if we wanted to find the error, all we would take is just 1 minus the accuracy. So if we just said 1 minus our accuracy, our decision tree was 21% inaccurate, or it had a misclassification rate of 21%. What that means is that it's these top right and bottom left quadrants here. And so our model predicted, for this instance, that a passenger survived when in actuality that passenger died. It misclassified it 14 times. In this instance, our D tree predicted that the passenger would die, but they actually survived 24 times. So if we were to take 24 plus 14 divided by the total, that would give us that 21% error here of our model. Another important thing to calculate when it comes to any sort of classification model are two other metrics. One's called sensitivity and the other specificity. So sensitivity is the amount of times that our classification model accurately predicted true values. So how many times did we accurately predict 1 when the actual value is 1? Well, it looks like we did that 48 times. So if we take 48 divided by 48 plus 24, our decision tree accurately predicted the true or the survived passengers 66% of the time. We could also use a function for that too. We would just say recall underscore score, and then we'd say y underscore test of survived, y underscore test of predicted, and then we'd say POS underscore label equals 1. And that'll give us the same 66% sensitivity score. So if we want to look at how many times our classification decision tree accurately predicted passengers that died, we would take 93 divided by 93 plus 14. And so if we did that, we would get 93 divided by 93 plus 14. And it looks like our classification decision tree accurately predicted passengers who died about 87% of the time. If you wanted a function that would do that automatically, you could just copy this recall score that we did for sensitivity. And then in the position label, you just change it to 0, and that'll change it to specificity. So you get the same 87%. So why are sensitivity and specificity important? Well, it's important to understand how good your model is at predicting whether something was like a 1 or a 0. In this case, our model looks like it's better at predicting passengers who died because the specificity is 87%, the sensitivity is 66%. And so our model is better at predicting passengers who died. So if there is ever some sort of tie, let's say, for a prediction, it's probably always going to side on the passenger having died because it looks like our model's better at predicting passengers who have died. Well, that was a really quick tutorial on how to build a classification decision tree. If you found this video helpful, I'd appreciate if you could like and subscribe to my channel so you can see future content. If you want to follow along from the video series from the beginning, just search @reasonable data science and you'll find all the prior videos.